So in this video, we're going to cover the next two learning objectives, 6.5 and 6.6 on our Unit 7 test. All right, in 6.5, we're looking at behavior of accumulation functions involving area. All right, but the main thing you need to remember this is still our fundamental theorem, part 1. Because a lot of these have to do with finding the derivative of something that's defined as an accumulation function. So here we see that g is defined using an integral, so g is an accumulation function. When does g have a relative max? We know a couple ways to tell if something has a relative max, but the easiest way is the first derivative test. Which, if maximums look like this, all right, there are peaks in the middle, that's when your derivative goes from positive to negative. All right, so if we want to figure out when something has a maximum, we're going to take its derivative. Well, g prime of x, if we take the derivative of something that looks like this, we just take the x and plug it in, is the same as f of x. And we have the graph of f of x here. So if we're trying to figure out when the derivative of g goes from positive to negative, that's the same as when f goes from positive to negative, and that happens right there. So my answer is 1. That's the only time that my f graph, which is the derivative of g, goes from positive to negative, which gives me a maximum. 14, all right, we have our function. We're going to figure out when it's increasing. Again, like we just saw, if we want to figure out when something's increasing, we use the first derivative. So I need to take the derivative of this function. That's not too bad, because the derivative of the function, I just plug the x's in there. And now I need to figure out when this is positive, because if something's increasing, its derivative is positive. So I start off by setting it equal to 0. All right, I like the x squared being positive, so I'm going to change everything, divide everything by -1, and then I can factor. All right, so those are the places where it's 0. That allows me to make my number line. And I do test points. And if I plug in 0, I'm going to get positives. I'm plugging into the derivative, because I don't know if the derivative is positive or negative. If I plug in 5, I'm going to get negatives. And if I plug in -5, I'm also going to get negatives. So when is it increasing? It's increasing when the derivative is positive, which is this middle section here, -3 to 2. This problem, essentially the same thing. We're trying to figure out when it's concave down. Concave down is the second derivative is negative. So the first thing is to find the second derivative. I take the first derivative. That means I just plug the x's in. And I take the second derivative. The derivative of that is going to be 2x minus 2. All right, I set that equal to 0. I get x equals 1. That allows me to make my number line. Oops. And I'm plugging these into the second derivative because I want to know if the second derivative is positive or negative, because that'll tell me concave down. So I plug in 0, I get a negative. I plug in 2, I get a positive. So when is it concave down? All the way up until 1. So my final answer is D. Right, here we are given this graph. All right, and g of x is defined, again, as an accumulation function. We're going to find g of 4. Right. This one you could kind of do too much work, but g of 4, we're just plugging in x equals 4. And for that x, so really this is the same as finding the -1 to 4 of f of t dt. All right, so what is the area from -1 to 4? All right, remembering that any area below the x-axis is negative, so we're going to get -10 plus 6. There's two areas, this area here and this area here, combined, and we get -4. As the answer is just -4. All right, next we're going to look at applying properties of definite integrals. All right, so I did this problem in a video, but the basic idea is we can break down integrals into smaller parts. So right now we have the three numbers, -2, 5, and 8. And we want to know what is this area here. All right. We know from 5 to -2 going backwards, 5 to -2 is -12, so going forwards it's going to be +12. So this area is +12. And then we can work backwards from this to figure out what the green area is. So the first thing is, if there's constant multiples, we can pull that out so that 3 can come out. And then we can separate integrals over addition signs. All right, so our equation looks like this. All right, this is 3 integral from -2 to 8. All right, the integral from -2 to 8 of 2 is going to be, go backwards to 2x, 16 is going to be 20. Subtract 20 to the other side, that gets you 15. Divide by 3, that gets you 5. So the full integral from -2 to 8 of g of x equals 5. So from -2 to 8, we have 5. So what does that green section have to be? When you go from 12 down to 5, that is going to be -7. At this one, we're trying to find the area from -4 to 7. All right, so I like to break things up into triangles, semicircles, and rectangles, all right, as much as possible. I'd start with rectangles because it's the easier one. So there's a big rectangle here, that's a part of the area. All right, there's kind of 2 triangles here, and these 2 semicircles there. All right, so I figure out all these little individual areas, then I can worry about positive and negative. This is a 2 by 2 triangle, which means it has area 2. This one's the exact same. 2 by 3 rectangle has an area of 6. This is a semicircle with a radius 1, so pi r squared, pi times 1 squared, which is pi, but it's only half of a circle, so instead of the full pi, it's pi over 2. This is a circle with a radius 2, so it's pi r squared, it's 4 pi, but again, it's only half, so that's 2 pi. So now we just need to combine these. The stuff on the top is all positive, so all the triangles in the square are positive, so 10 is the whole number part, and then we're going to have to take the positive pi over 2 and subtract the 2 pi part. And that tells us B is the right answer. This one is kind of similar to 17, is that we know these individual pieces, but now we want to figure out this more complicated integral. We can break it up, we can pull any constants out, and we can break it up over addition and subtraction signs. So it's going to be 2 integral from 1 to 3 of f of x, all right, minus 3 integral from 1 to 3 of g of x. All right, so I split it up over the minus sign, and I brought those constants out in front. But we know that's 5. And we know that's 8. We get -14. And this one, we're trying to find the area from -9 to 5. So -9 is here, and 5 is there. All right, so just make sure you're not doing all the way to +9 just because it's part of the graph. All right, make sure you're actually looking at your bounds. But again, I want to break it up into triangles and rectangles. So there's a rectangle. There's a rectangle. And I could just make that one big rectangle. All right, and then I have 2 triangles there and there. All right, so this triangle is 1, 2, 3, 4 by 2. So a 4 by 2 rectangle, triangle has an area of 4. This one is 1, 2, 3, 4, 5. 5 by 2 triangle, that has an area of 5. All right, this rectangle is 3 by 2 is 6. This is 2 by 5 is 10. This is 2 by 4, which is 8. All right, now I just add up all these numbers. Let's see, 20, 25, 33. All right, and that's our final answer. All right, so that is our overall, our 5th learning objective, the second one of this video, are just using areas and our properties of integrals to figure out answers for integrals.